It's recursively doing further and further each layer, some level layer.
Was the base case included?
And then it's done.
Yeah,
That's the base section.
yeah,
Yeah, just when it's done. It's done. Like splitting. Yeah, so it's in whatever. We're not gonna recurse all more recursive functions at that point.
Okay, good morning, everyone. Thank you for being here. So last time we were talking about March sort. So today we'll continue our discussion. We'll implement March sort by ourselves. And we'll also talk about the time complexity. We will analyze the time complexity of March sort. And there is also an in-class assignment today, which is due just after the class. So if you look into week 3 module, you will see there is a reading on March sort, only one single page reading. Just go through that on March sort. There is also an in-class assignment on divide and conquer, where you will have, okay, I need to change the time limit. So in this, you have multiple couple of questions, 4 questions and one programming assignment or programming question on March sort, where you need to complete the March sort code and submit along with the completed code. You need to submit the screenshot of the output. So this assignment is due by 2 p.m. today by 2 p.m. And also in-class participation. That means I want to strongly encourage you to participate in the class during the lecture. And in-class participation January 24. You just need to briefly mention using in 1 or 2 lines how did you participate during the lecture, and it carries 5 points. So if you ask me any question, or if you have tried to answer, or if you have correctly answered a couple of questions, just mention that briefly. And if you participate, then you may expect 5 out of 5. Otherwise, you will get 0. It is this assignment is just to encourage you to participate in an active learning. So this is also due by tonight. And last week we had one scribe note assignment. So it is also due by tonight. This is the scribe note assignment on binary search and divide and conquer. So whatever note you have taken, it may be digital note, it may be handwritten note, you just need to submit that. And only thing, just make sure that I can read whatever you have written. Okay, that's all. Okay, so we'll first start working on this in-class assignment 2, and there is a time limit of 60 minutes. So before you start, I just want to change the time limit so that you don't face any problem. At the same time, okay. So first thing, I suggest you to read this tutorial on March sort. It's just a single page tutorial. Just briefly go through that. 2 more minutes. Okay, I hope you have got enough time to go through this. So what are the points that that you think is important to point out?
One thing that I read on the bottom that's a little different than binary search, where binary search needs to be done on like a sorted array. For merge sort, it gives the same exact time, whether the array is sorted or not, because no matter what happens, it splits it individually and then back. So it's gonna take the same time, whether it, no matter kind of what way it's presented.
Okay, good point. I'll get back to that point at the end. Okay. Okay, what else? Yeah, the space requirement. So when we analyze Mars sort today, we'll also talk about the how much extra space it will require, which is proportional to n. N is the length of the array or the size of the array. So space requirement is also there. You need that much auxiliary space or additional space. Okay, good point. What else?
The runtime is big O and log n.
Big O n log n. It's the major point, I'd say. Compared to other algorithm like insertion sort is mentioned, big O of n square. Compared to n square, it is a major improvement. And the first lecture day, we talked about this comparison, n square versus n log n. So insertion sort, although here I think only mentioned, yeah, insertion sort, selection sort, bubble sort, all have time complexity n square, where n is the length of the array or number of elements or numbers that you want to sort. And here the time complexity is n log n, much better improvement, right? Even in many programming language has their predefined sorting technique. Although today we'll learn how to implement merge sort from the scratch, but when you do actual coding in any programming language, they already have predefined package to use sorting. And they follow different sorting techniques. Some programming language follows merge sort for their sorting. Some will use quick sort for their sorting technique as their sorting technique, or mix of some other techniques like combination of merge sort and insertion sort. It is also valuable mix of strategies, because merge sort needs merge sort have some overhead, like for recursive function call. Suppose you have very small array of size maybe 5 or 10. Why should you go for merge sort? Merge sort is great when you have a large array, but if the array is very small, go for simple technique like insertion sort. So this way you can come up with a combination of couple of sorting techniques. So we'll talk about that. Okay, what else?
If we have odd number of elements, then the left half has one extra element.
Yes, so it's a good point. So you have to make a strategy which would be same for every decision that you will make to calculate the mid. So whatever strategy you can come up with how to calculate mean, that should be same throughout your code. And obviously important part is this part, how you can perform merge sort. If the number of elements is 1, so an array of single element, so it is already sorted. So that is our base case. Else, recursively sort the right half, recursively sort the left half, and merge their solutions. So this is the pseudocode. Very simple, right? So this is the actual concept. Now today we'll look into the actual code, how to implement this strategy in C++. Okay. Okay, and the point Nathaniel pointed out. Okay, we'll talk when we'll discuss, we will analyze the time complexity of merge sort. That would be great. First, implement that. So the code is, so just download the part of the code. Just go to in-class assignment 2 on divide and, okay, let me share. Yeah, under in-class assignment 2, okay, there are a couple of questions are there. We'll solve it at the end. First, go to question number 5 and download the code mergesort.cpp. It carries 10 points. Okay, if you go to line number 79, the driver code, the main function. Inside main, there is an array. So this is unsorted, and we need to sort them. And this is the size of the array. We have already discussed last day. And first, I printed out the unsorted array. Then call the merge sort function and pass the array, the initial index, left index, and the right index. Okay. It is clear to you, right? Okay. Now let's move to merge sort. Okay, this is the merge sort code. So here, merge sort text has array, the left index, and the right index. So obviously the task 1 would be, everything would be when if the left index is less than the right index. So left index should be less than the right index. So first thing you need to calculate is the mean. How you can calculate the mean? So you have left index, you have right index. And obviously you need to divide the array into 2 smaller sub-arrays. So how you can do the division? You need to find out the midpoint, right? So what would be the mid?
Right plus left divided by 2.
Yeah, right plus left divided by 2, or the one we discussed last day. And don't put divide 2.0 or something. Divide by 2 will handle that odd number of elements, even number of elements by itself. Okay. So this way we come to know what is the midpoint. Now we need to break the array. So the initial array is ARR. It will be broken down into left subarray, right subarray. So you need to call the merge sort recursively and pass the whole array. And what else? So this part is to call the merge sort for left hub. And this line number 64 is to call the merge sort recursively for the right hub. So you have the whole array, you divide it into the middle point. Now call the merge sort function recursively for the left hub and the right hub. So at line 63, I'm calling merge sort for the left hub. How do I know which is the left part?
From it takes 0 to but is there like
Right. So array left to mid. So what I try to say, this is my initial array, AR. Okay. Now I find out this is the midpoint. This is my left index. This is my right index. Okay. Now I want to call the merge sort recursively for the left part, this part only, and this part. How do I know the size of this part? So the left would be same. Now this right would be here, would be the midpoint. And for this one, what is the left part? Mid plus 1. Mid is already here. So mid plus 1 to right. So I am passing the same array. Only I change the index. This way I will come to know which part I should concentrate. Okay. So at line 63, I call merge sort recursively for the left hub, Now I need to call at line 64 merge sort for the right hub. How can I call? So the same array needs to be passed as a parameter. Then mid plus 1, because mid is already considered here. So mid plus 1, and it would be right. Okay. Clear so far? Okay. Now I need to this one. So just assume that the left half is already sorted, the right half is already sorted. Now I need to combine their solution into one. So by calling the merge function. So merge will merge their solutions. So it will take array. At the same time, it will take left index and mid as well as the right index. So by these three parameters, it will come to know what is the, which portion is the left half, which portion is the right half, right? Through these three parameters, left, mid, and right. So that's why we need to pass these three parameters to merge. Clear so far? Okay. Now let's move on to the merge function. So this is the merge function. So this is the array. P is the left pointer, Q is the mid pointer, and R is the right pointer. Okay. Now what we did, N1 is the size of the left half. N1 here is the size of the left half. How do I know? Q is the midpoint, right? Mid minus left plus 1, that would be the size of the left. So first I want to know the size of the, so this is the left half, right? So I want to know the size of this left half. What would be mid minus left plus 1, that would be the size of the left half. So in this case, mid is I think Q, left is most probably P, Q minus P plus 1. Similarly, I need to know the size of the right half. So this is N1 and N2. So N2 is the size of the right half, N1 is the size of the left half. And I have, these are auxiliary array. Left is an auxiliary array, M is another auxiliary array to store the right half, and to store the left half. So L contains the left half and M contains the right half. Clear so far? Any questions? Okay, now at this point, from line 18 to 21, what we did is just to assign, just copy elements. So we created left half and right half and copied from the original array. That's all. And now our goal is to merge. So we have left array, which is L, we have right array, which is M. Now we need to merge them. So last day we discussed we need 3 index I, J, K. And while now this loop is saying that while none of the array is empty, that is I less than N1, J less than N2. So none of the left array or right array is empty right now. So whoever is smaller will go to the resulting array. Last we talk about the merging procedure. Do you need to revise that merging procedure? You know that, right? So whoever, okay, briefly. Okay. Okay. So the upper array is just the left array and the lower one is the right array. Okay. Oh. So the upper one just is the left.
You're muted.
No, I'm not muted. My video is off.
It's showing that there is a mute sign.
The video is off, I think. That's why.
Oh.
Oh, this one is this one.
Oh.
Yeah. I logged in from here. Okay. So, oh. Yes. So this is the left half, this is the right half. They are sorted individually. Now I want to combine their result into a resulting sorted array. So what I need to do, I need to compare the head of both arrays. Whoever is smaller will go to the resulting array. And we need to move on. So first 32 and 21 would be compared. 21 is smaller, so it will be placed in the sorted array. Then compare 32 and 55. 32 is smaller, 32 will move to the resulting array. Then compare 55 and 74. 55 is smaller, it will go to the resulting array. So to implement that, we need 3 index, I, J, K. I for this array, J for this array, and K for the resulting array. Okay, and we will compare ith index of this array with jth index of this array. Whoever is smaller will go to this kth index of the resulting array, right? So the same thing we are doing here. We have taken I, J, K, and while I less than N1 and J less than N2 means both left half and right half are not empty, and whoever is smaller should go to the resulting array. Resulting array is array of K. So whoever is smaller should go. So array K, what value you need to assign here? Li, because Li is the smaller. Li. And increment I, right? So now I will point to the next element in that array. Else means Li is greater than Mj. So which value will be assigned here? Mj. And increment J. And at the same time increment K. Clear? Now this is when both left half and right half are not empty. Now, if one of them is empty, what will happen? So suppose while I less than n1, that means that left array is not empty. That's why I less than n1, but the other array is empty. Clear so far? Because when we will be at line 44, that means this condition doesn't hold. This condition at line 31 doesn't hold. Only then we can reach out to line number 44. And at line number 44, it will be true when the left array is not empty, but the right array is empty. So if one is not empty and another one is empty, just copy their elements into the resulting array, right? So array K is just Li.
But we will always use the while loop, right? After finishing the first while loop, we can always use the second while loop.
First means at line 31.
Yes, 31. If
Yeah.
it is like true, even if it is true, then after finishing that while loop, we can still reach the.
No, loop means it will continue. It will continue. In every iteration, it will continue. At the end, that loop will break when the condition doesn't satisfy. At the end, this condition will not satisfy. Only then your control moves from 31 to 44. At line 31 to 44, the control will move only when the condition at line 31 is not true, right? And when it will be not true, when either one, because this is the AND operator, either one is false, either one or both false. So either I less than n1 is false or j less than n2 is false. Either one is false, it will not, the whole condition will be false, right? Is it clear so far? Okay. So at line 44 will be executed when the right hub is empty, but the left hub is not empty. Then the condition will be true. So that's why every index, every element of the left array will be assigned to your resulting array. Okay. Clear so far? Similarly, at line 50, the condition that is j less than n2 will be true only when the right hub is not empty, but the left hub is empty. So right hub is not empty, but left hub is empty. So just copy the elements of the right hub to your resulting array. So array K equals to right array is M, index is J, and increment J and K. Clear so far? So this is the merge procedure. Clear so far? Any questions? End means at what line?
61 through 67.
Yeah, this one. So is it clear so far?
I'm like not able to imagine this part of the equation. Like
These two, right?
yes.
Yeah. To understand it, you have to take small example. Then you may understand it. Suppose this is your initial array. Okay. So first time you will find the midpoint and you will get this part. This is your left part. This is your right part. First time these two lines will give you this. Now merge sort 63 at line 63. So it is recursive call. So when you when this function for the first time call this one, control goes to this function. Okay, this line 64 will not be executed at that time. So although I am saying the left hand and right half at the same time, right half will not be executed. First this left half. Again, this function will be called with these two indices. So what will happen? This function, in this function, you will also calculate mid and get this left half. So 12, 2, and now you have 12. Okay, so this is at this point when you recursively call for this array, it will go to this part left less than right. You mid equals to okay, merge sort left mid. And
There is no base case.
okay, base case. Okay, this is actually base case. This is actually working as a base case. So when you pass this one, the left and right are same. So this part will not be executed. So it will just return back to the calling function. Okay, so it will return back to calling function here. So left part is already done. So now it will move to right part. And you will call the recursive function for the right half. So it will be like this, return back. And now these two parts is already executed. Now you are calling merge only for these two, 12 and 2. This is your left array, this is your right array. So this is left array, right array, calling merge. So you are merging only 12 and 2. So you will eventually get 2 and 12. Now it is done for this part. It will go back, the control will move back to the calling function. Now this right part will be executed. So 15, 1.
Why did that transfer happen from 12 to 2? Like
12 to 2. This is merging.
no, I get that part, but like initially our 12 was the left part. Why the 2 became the right part? No, why not the 15 and 1?
At this point,
Yes. Like, yeah.
at this point, 15 and 1 is not executed. You are doing merge call.
Yes.
You are calling this merge sort recursively.
Yes.
So, okay.
How was it going from 63 to 67 without initiating 64?
60.
From 60, so like the merge sort, the first time we called the recursive at 63, like I'm with you there. But why is it skipping the merge sort of 64 to start merging that sub?
No, not skipping.
So
This
they're
one.
both happening and
Yeah, they-
okay,
yeah.
I'm with you.
So first, okay, let's merge sort the array A. Suppose what is the index? Left index is 0, 1, 2, 3. So left is 0. What is right index? 3. So first time it is called. Okay. So you calculate mid. Next time you call again merge sort. Pass the array. What is the left index? 0. What is mid? Mid is just assume 1. Okay. So merge sort is being called only for this part. Okay. Only for this part. Now again, it will call back to the same function and you will calculate the mid again. What is the mid? Maybe 0 or something.
Yeah.
So it will call merge sort A 0, 0. Mid is 0. That means it is only the array with single element. It is if left less than right. So it will, the condition will not satisfy because both are same. So it is done actually. So done means it will return back to here. At this moment, line 64 will be executed. At this moment, line 64. So far, we have already talking about 63. Since this part is returned back, this part is returned back because of line 63. Now 64 will be called for the right half. So here again, MS A. What is the right half? Mid plus 1. That is index 1. and right is also 1. So that means only this part. Again, left less than right will not satisfy, so it will return back. So it will return back to the calling function.
Why was the right one not 3?
Which one?
Why was the right 1 not 3? Like you said, A1, 1. Why not A1, 3?
Okay. Because of this. Here, this is the calling function. So here, this is left, this was the right. At this moment, just think this is your initial array. So this is the left index, this is the right index. That's why it is 1, not 3.
So the array that's getting passed in 64 is now the modified subarray.
Yeah,
From
modify the
63.
subarray because it
Okay,
is recursively called the same function. Only changing the left index and right index. You are with me so far? So A11 means only this part. It's a single array, array with single element, so it will return back. So it will return back means it will, this part will be wiped out. Now line 67 will be executed with containing left, mid, and right. Means this is one left subarray, this is right subarray. Now goal is to combine their result. Okay. So after combining their result, you will get, after line 67, you will get this part 2, 12, because right after executing line 67, you will get 2, 12. Then it will return back to the calling function. So this part will be wiped out from the memory. Now the right half will be executed. Here you need to take small example and draw it by yourself.
So this time like A2 to 3 will be called, right?
Okay, here it will be called A to 2 is the left index and right index is 3.
It will keep on going.
Yeah, it will keep going on. Okay, so now only this part will be executed.
And then the 2 elements and 2 elements will be merged at the end.
Yeah, first it will break down this array into smaller parts until you have array with a single element, and single element will not satisfy this condition. So it will return back to the calling function. Okay. So you just need to use another example and draw it by yourself. And do this step. You first call mark sort. This is the array, and what is the left index and what is the right index. Even you can print out here. You see out what is the left index, what is the here mid, what is the mid plus 1, what is right. Use print statement before 63 and before 64. This way you will understand, and use a small initial array. The initial array, make it very small, and use 2 print statement before this line and before this line, even before this line. This way you can understand how the call has been made, how the index has been changed.
Well, my last question is like, so once it's sorted from 2 to 12, how does the merge sort function know to start at 2? Like, how does it now discard the left half and now focus on the right half?
Okay,
Using that logic that's there.
because of this line 64.
Okay,
Because of 64, 63 is for the left part. Because of 64, it will know that mid plus 1 is my left index, that is 2 here.
well, I just mean like, so like once we call the left sub arrays into merge, right? Why are we not back at looking at 0 through 3 and chopping, and then we're trying to resort again 0 and 1 as opposed to 2 and 3? Like, what is iterating it to the right half of? I may just mean misunderstanding how this is working. I'm not sure.
Okay. This way you need to take the example first. Otherwise, if you skip any step, it would be difficult. Like here, First A03 will be called.
Uh-huh.
0 index is the left index, 3 is the right index. Then I have shown merge sort A0. Now mid will be the right index. What is the mid index? The right index is 1. It will be called.
Right.
So only this part will be called.
Mhm.
Okay. Next, MS A. Okay, 0. Okay. For this part, you need to calculate the mid again. Okay. And it is 0, 1. So 0. Suppose the left part is 0. Okay. This is the mid point. So that means it is only focusing on this array with single element.
Okay.
Up to this point. Okay.
Mhm.
Now, left less than right. At this moment, left and right both are same. So that condition will not satisfy, right? So that means the control goes back to the calling function. At this point, it is clear. That means the space allocated for this will be wiped out from the memory. So this is for 63. Now 64 is there. Array mid plus 1 to right. So mid plus 1, that is 0. So it will call merge sort A 1, 1. So only it will focus the right part. So right part means this one. Okay. Now this is a single element array with single element. That means this condition will not satisfy line 59. So the control moves back to the calling function. Clear so far? So that means this part will be wiped out from the memory. At this moment, merge will be called to merge the solution of this hub with this hub. Clear? So it will become 2, 12. Okay. After merging.
Okay.
After merging, it will become 2, 12. So at this moment. Okay.
Mhm.
Then, so this is already done. So it will, the control moves back to the calling function. So this part is done. This part is done. So this was the calling function. Okay. The main function, the first merge sort call. And everything what we discussed, the first started from line 63.
Mhm.
Now I will go move to 64.
Okay, I'm with you.
Okay.
Yeah.
Now I'll go to
Okay.
64. 64 is saying that now I need to focus. So far we have focused on the left hub. Now I will focus the right hub. According to 64, how I can focus right hub? Array. So I need to call merge sort with array and mid plus 1. Mid plus 1 is 2 and right is 3. Now I'm moving focus. I'm moving my focus to right hub and repeat the same thing. Repeat the same thing. So finally I will get, here I already got 212. Here I will get 150. Okay. And finally at the end at line 67, we will merge these two solutions.
Okay, I got you now. Thank you.
Just take an example and do it by yourself. Okay. Good. Okay, merge sort. So again, for merge sort, first I need to calculate the mid, then call the merge sort recursively for the left hub, call the merge sort for the right hub, and merge their solution altogether. That's the step that you need to follow. Clear? Okay, is there anything that we are missing or we are done? What happened? Some bracket is missing. It is. Okay, is there any error expected bracket? What is, oh. I don't know why the error was showing previously. I did not do anything. Okay, so first unsorted array is printed here, and this is the sorted array. Yes. Line 16.
Yeah.
One six is important to know the space complexity. How much auxiliary additional space it needs, particularly this implementation. So these two, this is for left half, this is for right half, and we copy it. So this is additional array that you need, right? So the space complexity depends on this line 16. So you need additional array L, additional array M. And what is their combined size? N1 plus N2. And what is that? N1 plus N2. Size of the array, right? Because this is my whole array, we divide into two halves, left and right. So their combined size would be the total size of the initial array. So the space complexity is proportional to the size of the initial array. That is proportional to n. And how this line illustrates that. Clear? So this is space complexity. Any questions so far? Yes. In your case? I don't know.
So like, that's the thing, what's merging. Yeah, we put that because that was finished its rehearsal, then we're gonna.
Always have so
So the board will work. I think it's
Basing out software.
I think so.
It's a lot different.
Like I'm trying to find my house items here too.
Or you can use any online compiler.
But on the online side, it just works.
Okay, okay.
It's a little C++ compiler,
Yeah.
whatever.
Okay.
Yeah.
Any questions? See, to totally grasp the concept, what you need to do, you need to dig deeper into the code. And how you can do that? Just use couple of print statement to visualize what it is printed after executing every iteration. So my suggestion would be at your spare time, just before line 63 and just before line 64, put a print statement. So whatever I have done here in this stack, that part would be printed there. So see what is the index. This is left index, this is the right index. What is the index is being printed here. It will clear your concept. Because recursive function is, that's why it is very useful to avoid that complexity. There is much complexity is behind that, but only using these two lines, you can avoid those complexity. But to grasp the whole concept, first you need to dig deeper into that, because it is a recursive function. You will call the same function multiple times with different parameters. So do it by yourself, spend some more time, the concept will be clear. And this is one of the most important sorting technique. That's why I spent couple of some time. Okay. Next. So this is the whole algorithm or pseudocode for merge sort. So if number of elements is equals to 1, so if an array contains only a single element, so it's already sorted. You don't need to do anything. Otherwise, call the merge sort for the left half, call the merge sort for the right half, and combine their solutions altogether. That's all. So now let's discuss about the time complexity. How much time it will take. So if you derive the recurrence relation, okay, let's do it here. So if we derive the time complexity, so Tn, so what we are doing, we are calling merge sort for the left half. So this is your initial array. We are calling merge sort for the left half. We are calling merge sort for the right half. So what is the, suppose the initial array is of size n. So what is the size of left half initially? N by 2. What is the size of the right half? N by 2. So the time Tn is the total time to sort the whole array. It depends on the time that you need to spend to sort the left half plus the time you need to spend to sort the right half, right? Clear so far? So how we can do that? First, we need to divide the whole array into left half and right half. Divide until you have array with single element, right? Plus, you need to combine their solutions altogether. So Tn is actually depends on 2 Tn by 2. Why 2? This is 1 Tn by 2 for left half, another Tn by 2 for the right half. Plus, they are combine their result, combine their solutions. That is merge function. And how much time it will take? N. Last day we discussed N. So this part you may think for division or divide, and this part is conquer. So the recurrence relation is Tn equals to 2Tn by 2 plus n. Sometimes people use Cn. C is some constant. Why C? Because you need to calculate what is mid. You need to check the condition of while loop, those things. So some other time will be involved, but they are constant, no variable. And our goal is to check about the variable, because constant is always constant. So here C is a variable. So if in your assignment, there is a question that what is the recurrence relation of merge sort, you need to give Tn equals to 2Tn/2 plus Cn. It is still incomplete because this is true when n is greater than 0. Or I would say n is greater than 1. Means there are more than one elements in your array. Then you will divide, right? If their array contains only a single element, you don't need to divide it, right? So this is one. Another would be 1 or constant when n equals to 1. So Tn equals to 1 when n equals to 1. Means the array contains only a single element. Then it's a constant time, right? Otherwise, if the array contains more than one element, then the recurrence relation would be Tn equals to 2Tn/2 plus n or Cn. So this is the recurrence relation for merge sort. Now, how we can derive time complexity using this recurrence relation? Let's derive that. So Tn equals to 2Tn/2 plus n, right? Now, can you divide it further? So we'll break it further, right? So now the problem is that this is the left half of size n/2. We'll divide it into two half again of size n/4, n/4, right? So it would be 2Tn/4 plus n. Right? We just expand Tn/2, this part. So what is that? 2 square Tn/2 square plus n/2 multiplied by n/2 would be n plus n, that is 2n. Clear? This part is clear. Are you convinced they are same? So what would be if we still divide this part Tn/4? It would be n/8, right? So it would be 2⁵ Tn/2⁵ plus 3n. Are you with me so far? Similarly, it would be 2⁴ Tn/2⁴ plus 4n, and so on, right? So after k step, it will be 2⁵ Tn/2⁵ plus kn, right? Clear so far? So let's assume after k step, it becomes T of 1, means array of single element, so that it reaches the base case. So we have discussed this is the base case. So constant time. So after k is a variable, let's assume after k step, it reaches the base case. So this part will be T1. So n/2⁵ becomes 1. Then this T1 would be 1. At that point, T1 would be 1, right? So when n/2⁵ equals to 1, so last we did n equals to 2⁵ or log n equals to k. So the value of k is log n. That means after log n step, you will reach this base case, that is T1. Clear so far? So just put the value of k in this equation. So 2⁵ k means log n. T of 1 plus n log n. Clear so far? Now 2 to the power log n, what is that? Here base is 2,
And
n. T1 is constant, that is 1. So n plus n log n. Clear so far? Clear? Now, when we calculate, when we derive or big O of something, time complexity, to calculate the worst case time complexity, when we derive the big O of something, we will focus on the larger term. So here two terms are there, n and n log n. Which is the larger one? Which is the larger term, dominating term?
log.
N log n. N log n is the dominating term, right? So we will ignore this part, the smaller term. Just think n is 1 billion or more than that. At that time, you see, this part is the dominating part. We will ignore this part. So it will be similar to n log n when n is very large number. When n is very large, like 1 billion or more than that, then this is the dominating part. So the time complexity is order of n log n, and the base is 2. Clear so far? And why base is 2? Because we divide the problem into 2 halves. Sometimes in your interview, they might ask you, okay, instead of dividing into 2 halves, why not divide into 3 halves? Will it help you to improve the performance? Why?
Because you still have to perform that division on every part.
So the time complexity in that time would be order of n log n, the base would be 3. So just ignore the base. When n is very large, you don't care about the base. What is the base of log? So it would be still n log n. If you divide into 3 halves instead of 2 halves. Clear? So the time complexity is order of n log n. So this is one way to derive that. Slightly complicated way.
If we increase the base from 2 to 3, will it increase the time complexity or decrease it?
Decrease.
It will decrease.
Decrease, but when n is 1 billion, it doesn't matter actually. Because always we think about large number. When n is very small, like 5 or 10, it matters. But when n is 1 billion or more than that, 100 million, that thing, or 1 billion, then that base doesn't matter actually. Almost same there. So this is one way to derive the time complexity of merge sort from the recurrence relation. Another way you can do, last day we discussed, suppose this is your initial problem of size n. Next time you divide it into 2 sub-problems of size n by 2, right? You further divide into 2 sub-problems of size n by 4 for this part, and n by 4 for this part. And you will continue doing this, right? Until you have an array of size 1. Right? Clear so far? So what is the height of the tree? Height of the tree. Log n. How to derive that? Same way. Just assume. So what is after 1 iteration, it becomes n by 2. That is n by 2 to the power 1. So n becomes n by 2 after 1 iteration. It becomes after 2 iteration, it becomes n by 2 square. After 3 iteration, it becomes n by 2 to the power 3. Let's assume after k iteration, it becomes n by 2 to the power k. And also assume that after k iteration, it will become an array of single element. So n by 2 to the power k equals to 1. And we have already discussed, if n by 2 to the power k is 1, then n equals to 2 to the power k. If you take log in both sides, then k would be log n. That means after log n step, the problem of size n will become a problem of size 1. So the height of the tree is log n. That is clear. So height of the tree is log n. So height is log n, the base is 2. Now in every level, so this is one level, this is another level, this is another level. In every level, how much work you need to perform? That is only the merging. You just need to merge the solution of the left half with the right half. So in every level, you need to perform merging, and merging is order of n. So in every level, you need to perform order of n operation, and total number of levels is height, that is log n. So total time is log n multiplied by merging time in every level, that is n. So total complexity would be order of n log n. So this is the recursion tree. Using this way, you can also derive the time complexity of merge sort. And for many problems, we'll repeat the same strategy to derive the time complexity. It is very important to understand. And the same strategy we'll use, that after k iteration, you need to come up with a generic form. After k iteration, it will reach the base case. And now you need to find out what is the value of k. If you understand this part, the time complexity that derivation would be very easy. So clear so far? Okay. So in your assignment, so question number 5 is already done. So question number 4. First, let's talk about question number 3. So it is asking for the recurrence relation of merge sort. Recurrence relation of merge sort. So which one would be the correct answer? B, right? Tn equals to 2Tn by 2 plus Cn. Here C is a constant. It is also given here. C is a constant. Okay, so question number 3 is done. Now, question number 4, the best and the worst case time complexity of merge sort. So C, B or A. It is asking for best case, worst case. So the time we derive, whatever we derived so far, is it the worst case or it was the best case for merge sort, or both?
Yeah.
Both. Because in case of merge sort, average case, best case, worst case, all are same. You need to perform the same task. It doesn't matter whether your initial array is already sorted or not. That Nathaniel pointed out in that tutorial. And the bottom of the tutorial, it was mentioned. Suppose your array is already sorted and you want to perform merge sort. Merge sort, there is no way to know beforehand that whether the array is already sorted. So best case, average case, worst case, all are same for merge sort. So answer would be B, right? All would be n log n. It doesn't matter whether it's a best case or worst case. Next day, we'll talk about quick sort. Quick sort, the worst case would be worse than would be order of n squared. Best case and average case would be n log n. So we'll talk about that. But in case of merge, all are same, n log n. So question number 3 and 4 are done. And now the question number 1, recurrence relation for binary search. A, right. It divides the problem into one half. Means divide into two half, but you will discard one half. So you will focus only either left half or right half. That's why Tn equals to Tn by 2. That's the difference between merge sort. In case of merge sort, you need to focus on both halves. You cannot discard any half. But in case of binary search, you will focus either left half or right half. So A. And order of binary search algorithm, the time complexity would be log n or n log n. Which one? C, log n. It is log n. Okay, we are running out of time. Briefly. Okay, briefly, let me tell you. Okay, so merge sort versus insertion sort. So as you know, insertion sort takes order of n squared, right? So if in this table, you can understand the comparison between insertion sort and merge sort with different value of n. When n is a very large number, 2 to the power 20, the performance, the time difference, so the ratio is almost close to 0.0004. Merge sort takes this amount of time, insertion sort takes this amount of time. So you may look in, you may understand that when n is very large, n is increasing, the difference between the performance difference between merge sort and insertion sort is also increasing rapidly. That's why we need n log n strategy. And if we think of sorting and searching, that if we need to perform binary search, there is one condition that the arrays should be sorted, already sorted. Then you can apply binary search. So one thing you can do, if the array is unsorted, you can first apply merge sort, then you can apply binary search, right? It's possible. And the overall time complexity would be, this is the time complexity for merge sort to sort the array, plus this is the time for binary search. Now, which one is the dominating part, larger part? N log n. So ignore this smaller term. So overall time complexity would be n log n. If you apply merge sort, if you apply insertion sort, then overall time complexity would be order of n squared plus order of log n. And this is the dominating part. So overall time complexity would be order of n squared. So this is another way to apply, first apply merge sort to make the array sorted, then apply binary search for searching. So obviously order of n log n is much more efficient than order of n squared, and the performance is always guaranteed that you will get order of n log n performance every time. Worst case, it may be average case, it may be best case. Whatever it is, whatever your input is, you will get this guaranteed performance, and suitable for extremely large number of inputs. Because if your array is smaller, then why should we take care of the overhead? Recursion means overhead. So to avoid that, you can focus on insertion sort, selection sort, bubble sort, if your array is smaller. Even, sorry, I'm out of time, but still I would like to let you know that when we are dividing in merge sort, we are dividing the problem into smaller problems, right? So when we should stop, when the array is of size 1, right? So why should we reach 1? We can stop that division when array will be of length maybe 10. Because array of 10, insertion sort will perform better than merge sort because of less overhead. So it would be a combination of merge sort and insertion sort, means you will divide, and when you reach an array of size 10 or something like that, you will stop division and apply insertion sort for that, to make that smaller sub problems into to solve that smaller sub problems. So it will be a combination of merge sort and insertion sort. It will improve the overall performance. Theoretically, performance would be same, but practically the performance would be better. Okay, next day we'll learn another sorting algorithm, which is called quick sort.